All right, back to the task that we had at hand, which was, I said, that we could define the average x velocity as displacement divided by time interval. And the graphical interpretation is if we make a graph of the position on the x-axis as a function of t for the motion of an object, then if we look at where it is on the graph at t0, and also where it is on the graph at t1, and we connect those 2 points with what's called a secant line, the average x velocity is nothing other than the slope of the secant line on the x versus t graph. That's kind of a mouthful, but we'll get used to saying it. Nobody cares about the average x velocity. For us, it's just a stepping stone to the instantaneous x velocity. When if I go on a trip that's an hour long, I don't really care most of the time what my average speed was when I'm going on the trip. What I want to know is, right now, am I breaking the speed limit? What's my instantaneous speed? Or in this case, we'll talk about the instantaneous velocity. So it corresponds not to a time interval between t0 and t1, but at some particular time, like t0, or maybe this time over here, or this time over here. The definition of the x velocity, or sometimes called the instantaneous x velocity, it only corresponds to a single time, t0, is, well, all you do is take the average x velocity, delta x over delta t, but you do it over a very tiny time interval. In other words, instead of going from t0 to a much later time, t1, I go from t0 to a really close time, t1. And that's what this symbol is here. If you've never taken calculus, you may not know this symbol. It's called a limit symbol, but it just means see what the trend is. In other words, see what the limiting behavior is of this ratio as you let delta t get smaller and smaller. So in other words, you have some time in mind that you're interested in. In this case, we're interested maybe in what is the x velocity at t0. What I'm going to do is take delta x over delta t over a very tiny time interval that starts at t0 and goes to a time that's just a little bit later. So, for example, I might, instead of making my t1 over here like it was before, I'm going to move t1 a little bit closer and take that slope of that secant line. And then I'm going to take that t1 and move it a little bit closer and a little bit closer and really, really close to t0, and let's see what the trend is. And what I want to think about is what does it correspond graphically? It's not the secant line anymore, because for a secant line you need 2 points that are separated, that are connected by a line. But this graphic on the next slide kind of shows that as if you take a secant line between points that are closer and closer together, just like we did on the previous graph, but here it's showing it in animation, the secant lines, which are changing as you make delta t smaller and smaller, get closer and closer to what's called a tangent line to the graph at the particular time. Tangent line means just a line that in that little region only, instead of touching the graph at 2 different points, it only touches it at 1 point. So it's like you took your ruler and laid it up against the graph at time t0 here at point P. Okay? So in the same way, if I let that delta t get smaller and smaller, in other words, if I let this t0 get closer and closer and closer to t1, this secant line is going to get closer and closer and closer to what we call the tangent line to the curve at t0. Okay? And so here's the definition. The x velocity at time t0 is just the average x velocity computed over a very small time interval. And graphically, it corresponds to the slope of the tangent line of an x versus t graph at the particular time that you're interested in it at. Okay? So this only, whereas average x velocity needs 2 times, you're talking about an average between 2 times. Here you're talking about an instantaneous. It applies only at a single time. I didn't have room to fit it on here, but the speed is just the magnitude of the velocity. And at least in one dimension, it's pretty simple to do that. Whatever the instantaneous velocity is, the speed is, the instantaneous velocity is going to be positive or negative. If the instantaneous velocity is positive, that means you're moving in the positive x direction at that particular time. If it's negative, it means you're heading towards the negative x-axis direction at that particular time. To get the speed, we just throw away the minus sign. That's what this is saying. It'll be different in 2 and 3 dimensions. We have to think a little bit more, but in 1 dimension, it's pretty simple. All right, let's do, I think, a couple of voting questions having to do with velocity. Here's the graph of the position. So you can think of a train that's moving on the x-axis. So this is like x here versus t. I just borrowed this graph from somebody else where they had the axes labeled this way. X versus t graph for a train moving on a long straight track, essentially the x-axis. The graph shows the position as a function of time for the train, and which of the following is true for what you're seeing here? A, the train speeds up all the time. B, the train slows down all the time. C, it speeds up part of the time and slows down part of the time for the time that's shown for the graph. And D, it's moving at constant velocity. Try to use what we learned about speed corresponding to the slope of the tangent line to think about how to argue your way between these and pick out the only one that's correct in this case. Okay, if you're still thinking about it, what I want you to do is pause the video. I'm going to go on and talk about the answer now, but you should take the time to really think through all of them, stare at the graph, and decide on an answer every time we have one of these voting questions. The correct answer is it's slowing down all the time, and we can see that by using part of what we found out on the previous slide, which is Vx velocity is the slope of the tangent line attached at the time you're interested in. So at an early time, in the time region that's shown here, at an early time, here's the tangent line that we would attach to the curve at that particular time. It's got a pretty big slope. If we go to a slightly later time, notice the slope has decreased, right? Big slopes go up like this. Smaller slopes are like this, even smaller, and then we get to zero slopes and then negative slopes going down like this. So we start out with a bigger slope, smaller slope, still positive slope, right? It's going upwards. Still smaller. So we're going from bigger to less to less. That means the x velocity slows down. The x velocity is getting smaller and smaller and smaller, and that means that the speed is getting less and less. If your x velocity is getting closer and closer to zero because the slope of the tangent line is getting close to zero, then the speed would be getting close to zero too. So it slows down all the time. Here's a second voting question. Same situation, but here we have 2 parallel tracks. So the two long straight train tracks, and maybe the x-axis is drawn right in between the tracks, and we're going to mark their x position as a function of time. And we're shown the graphs for train A and train B as 2 separate graphs, their position as a function of time. Which of these is true? At time TB, which is marked on here, that's the time at which these 2 curves cross. Both trains have the same velocity, x velocity. B, both trains speed up for the whole time that's shown. Or C, both trains have the same velocity at some time before TB. So again, I'd like you to decide on your answer. If you need more time, just pause the video, but I'm not going to sit here silently too much longer. The correct answer can be gotten again from the definition. Vx is the slope of the tangent line. So we're looking at the slope of the tangent line to this curvy curve for train B and this straight curve for train A. If you attach a tangent line to train A's graph, the slope of the tangent line is going to be the same whether I attach it here or here or here. So the slope of A's tangent line isn't going to change no matter what time I choose. But I've just chosen some time t0 here. And, well, the first thing to realize that I didn't really illustrate on here is that at time tb, both trains don't have the same x velocity. If I attach a tangent line to A, it's going to be going up like this, whereas B is going to have a smaller slope. So the slopes of the tangent lines are different. They have different x velocities. Furthermore, both trains don't speed up all the time. B is false because B is doing exactly what we showed the single train doing in the previous one. It's slowing down all the time. The correct answer is C. Both trains have the same velocity at some time before TB. Here, at this particular time, T0 here, train A is going faster. The slope of its tangent line is bigger than the slope of the tangent line to B. At this other time, T0, which is pretty early, B has a larger slope of the tangent line. And if I choose the time just right, I can find a time somewhere in between 0 and TB where the slopes of the attached tangent lines are exactly the same, and that means those two trains are moving with the same x velocity at that particular time. It's kind of a lot but to fathom at first if you're not used to thinking about this stuff, but the more we practice with it, the more comfortable we'll be with it. Saying the words really helps. All right, let's do a worksheet now, which is kind of an extensive worksheet, so you're going to have to spend some time graphing on this one. The setup is we've got a mass that's been hung vertically from a spring. So I'm imagining I've got a little bar here, I attached a spring to it, and then here's a really massive piece of metal that I've attached to the bottom of the spring. And I pulled that mass down to a certain position and let it go. And it's slowly oscillating up and down under the influence of gravity and also under the influence of the spring force that's on it. So we're going to call when it was released time t equals 0. So time t equals 0 corresponds to when this is at the lowest position. That's when we let it go from rest. And we're also going to call that x equals 0. So we're going to label with the position of the bottom part of this mass, the x value that we're going to keep track of. So notice when we released it at time t equals 0, the bottom of the mass is at x equals 0 on the x-axis that's here. And what we want to do is, positive x is upward in this case. We want to graph x versus t and vx versus t on the axes below for 2 complete oscillation periods. So that means going up and then down and then again up and then down. Show 2 complete oscillation periods. And here on the time axis, I'm showing when we released it, it was at the bottom position. Sometime later, it's again at the bottom position, and sometime later still it's at the bottom position. If you fill in that, you'll have done 2 complete oscillations. Same thing on the Vx versus t graph. We're going to try to make a graph of what is Vx as a function of t for this particular case. So what I want you to do is take out your worksheet. Hopefully you have a printed out copy, but if you don't for these, you can always just take out a piece of paper, copy the graphs onto your paper, and work them out. And we're going to pause the video, not pause the video, end the video here, and the solution to this will be given at the beginning of the next video. That's, in a lot of cases, how we'll end and start videos. So I'll see you in the next video. Good luck with that. It'll all be explained, and you can compare with your solution in the next time.